Welcome to Manish Kumar channel. Today we are going to discuss about the linear transformation. Okay. So what is the definition of a linear transformation? Let V and W be two vector spaces over the same field. Same field is important here, and the transformation L from V to W be a function or map from V to W. That is, for each vector V is in capital V, so LV denotes the exactly one vector of W. Then L is linear transformation if and only if the following two conditions are true. L of V1 plus V2 equal to L of V1 plus L of V2 for all V1, V2 is in V, and L of alpha V equal to alpha times of L of V for all alpha. Alpha is a scalar here, right? A scalar coming from the field. Okay. And for all vector V is in V. So here same field is important. It means if V is defined on the real field R, then W must be defined on the real field R. So field must be same for both, right? Same field. Then a linear transformation has some meaning. Okay, this is very important. Okay, so when we call the linear transformation as a linear operator, if the domain and codomain both are same as V, right? So it means that suppose if you have a linear transformation L from R3 to R3, and then L of X, Y, Z equal to X, Y, Z just as an identity transformation, right? Then this becomes a linear operator because range is going to be codomain and domain. Both are same, right? Domain and codomain both are going to be same. Okay. So this is called a linear operator. Or in other word, you can say that V equal to W, right? Domain and codomain are same. Then we can say that this is a linear operator. Okay, V equal to W. So there is one result. Let V and W be vector subspaces over the same field, right? Um, I'm not writing again and again, but the meaning is that over the same field. And L is a linear transformation from V to W. And let 0V, 0 suffix V denotes the 0 vector of in V, and 0 suffix W denotes the 0 vector in W. Then L of 0 vector of V equal to 0 vector of W. It means 0 map to 0, right? First property says. Second property says L of minus V equal to minus L of V for all V is in V, right? Or in general, the linear combination is going to be same as the alpha 1 L V1 plus alpha 2 L V2 and so on plus alpha n Vn for all scalars in R and for all vectors in V, right? So it means that it is sufficient to check these two conditions for a given linear transformation. So 0 maps to 0 and minus of V, L of minus V equal to minus of V. Okay, these two conditions are, if L is linear, then these two conditions must hold. Okay, another result, V1, V2 and V3 be vector spaces such that the map L1 from V1 to V2 L2 from V2 to V3, all are the linear transformation. Then composition map L2 composition L1 from V1 to V3 is given by this, right? L2 composition L1 is equal to L1 of V and L2 of V, right? For all V is in V1 is again a linear transformation. Okay, so it means if you have vector space V1, if you have a vector space V2, and if you have another vector space V3, then L is from V1 to V2, L2 is from V2 to V3. Then I want to know the transformation from this direction. V1 to V3 is nothing but L2 of L2 of L of V, right? Because you see L2 and then operated on L1V will be the composition map. We write it as L2 composition L1 of V. Okay, so this is a composition map is also a linear transformation, right? Another important result, if you see, L is a linear transformation from V to W, and V dash is a subspace of V. Then subspace can be defined as then L of V dash equal to L of V, all V is in V dash, is an image of V in W, is a subspace. It means subspace map to subspace. If you have V and if you have V dash and if you have a linear transformation W and W dash, right? Then basically this is W dash. Then basically this map, this V dash map to V dash is a subspace of V. Then V dash map through linear transformation L, right? L of V dash. L of V dash means all those vectors sitting here in V such that it maps to a subset of W called W dash. Then we can say that this is going to be a subspace. This W dash is a subspace, right? And which is an image of V dash under L. Okay. And in particular, the range of L is a subspace of W. So this is going to be the range and then is a subspace of W. Okay. If W dash is a subspace of W, then L inverse of W dash. L inverse is nothing but here the pre-image, right? Pre-image of W dash. Pre-image of W dash will be in here. So L inverse of W dash equal to all those V's in V such that all those V such that L of V is in W dash. So pre-image of W dash in V is a subspace, right? You can pull back the subspace using the inverse transformation, right? Pre-image basically, right? Here this inverse, L inverse is nothing but the pre-image, not the inverse transformation 1, 1 and 2. So this is very, very important point. You have to make sure that this is just the pre-image, right? Not 1, 1 and 2 invertible transform. Okay, we are just looking the image of W dash in V, pre-image of W dash in V. Okay, both are subspace. It means subspace pulls the subspace, right? Let us see some examples. So L is a vector, L is a linear transformation from V to W. The zero map, L of V equal to 0 of W, right? For all V's in V. Then this is obviously a linear transformation. You can check L of U plus V is equal to because of the property of fact that this goes to 0 of W. right? So this can be written as 0 of W plus 0 of W. This can also be written as L of U plus L of W, L of V, right? So first property, L of U plus V equal to L of U, L of V. Secondly, if you say L of alpha of U is equal to 0 of W, and 0 of W is something called alpha 0 of W, that means alpha L of U. So alpha U equal to L of alpha U for all alpha belongs to real field. Okay. And here for all and for all U belongs to V. So this is true basically, right? So for all U, V belongs to V, L of U plus V equal to L of U plus L of V, and L of alpha U equal to alpha L of U. So this is a linear transformation. Similarly, the next map, L of L from V to W be an I map defined as lambda of V. Lambda is a fixed scalar for all vectors V. So this is also, you know, a linear transformation you can easily verify, right? Called the scalar multiplication. Okay, means you need to check two properties. You can see 0 map to 0, minus V equal to minus of lambda V. Both properties are satisfied, right? Or you can check the linearity property as well as this, two properties of the linear transformation. Another example, V equal to V means identity map, LV map to V, right? This is an identity map. So this is also a linear transformation. Another example, L from R3 to R3, L of XYZ equal to XY0 for all vectors XYZs in R3 is called the projection map. This is also a linear transformation, right? So now the next example, L of R3 to R3 be the map. Let L of R3 to R3 be the map as X, Y, X1, X2, X3 equal to X2, X3, X1, right? Is also linear transformation. So verify. It's very easy to verify, right? Both the properties. Similarly, let L is the map from set of all 2 cross 2 matrices to 2 cross 2 matrices over the real field defined as L of A, B, C, D equal to the 2 cross 2 matrix with some setting, right? So this is also a linear transformation. You can also verify. Now let us do some more problems. Determine which one of the following functions are linear transformation in between, right? So H from R4 to R4 given by X plus 1, X2, X1 plus 1, X2 minus 2, X3 and X4. So this any constant is going to make our life in trouble, right? So we have to be very careful because if you see here, this is the constant. If you add 2 times just the 2 vectors, it becomes minus 8. But we want always minus 4 here, which is not possible. So you can directly discard this is not a linear transformation, right? And even if you check 0 map to 0 vector, so 0 map to 0 vector is also not going to be satisfied. But provided H must be linear, right? So this is not a linear transformation because constant term or any tuple says I am going to greater than 0 or less than 0. So alpha scalar will be, checking that property will not be into that vector space, right? So this is not going to be the linear transformation. What about this? Answer is yes. Yes, this is a linear transformation. Okay. Uh, Assume if I add here 1 or something, then this is again going to be create a problem, right? So this type of things should not be there in the linear transform in the linear transforms. Okay. So now let us see by thorough method. So H is from R4 to R4. So I'm going to take it as H is given by this. I'm going to add the two vectors and vector wise addition, component wise addition. So I got this component wise addition, and then using the definition, first component plus 1, second component minus 2, third component, and then last minus 4. So one side h of u plus v type I have calculated. Now I have to see h of u plus h of v separately and then try to see whether they are equal or not. So if you see here h of u and h of v, so while adding these two we are getting minus 8. That is not at all equal. So this left hand side and right hand side is not equal. So this is not a linear transformation, right? Second part, if you see the I from M to 2 from M to 2, and then just you take element will looks like a matrix. You take A, B, C, D, A dash, B dash, C dash, D dash, and then try to check linearity property, right? So I of A plus B, and then you can calculate IA and IB, and then when you see both are going to be equal, so first condition holds true. Similarly, for any scalar k, you can multiply, right? And then you will get the same, right? So this is a linear transformation. And especially since if you see domain and codomain are same, so this is also called a linear operator. Okay, let us do one more problem. So L is a linear transformation from R3 to R3, and it is a linear operator. It means that codomain and range are same, right? Codomain and domain are same. Okay, so L of 1 0 0 is given by this, L of 0 1 0 is given by this, and L of 0 0 1 is given by this. So sometimes they will ask construct the linear transformation, right? And then here what they are asking, find the value of L of minus 1 2 4. So first we will find the linear transformation. Our job is to first construct the general linear transformation, and then we will plug these values to get the output of that. Okay, so how do we do that? Let us see. So since this is given already, okay, then general formula for constructing this. So L of x plus y plus z is equal to x times L of x 1 0 0 y times 0 1 0 plus z times 0 0 1, right? We will substitute these values. Already these values are given, right? Because L of x plus y is equal to L of x and plus L of y. This property we are using. Okay. So now if you see here, L of, because any vector can be written as a linear combination of this. So now if you apply L on it, alpha will play a role of x, beta will play a role of y, gamma will play a role of z. Then you are going to take out and then linear transforms will be applied inside. L of alpha x is equal to alpha times of L of x. Okay, so this property using linearity we can write, and these values are already available. These values are equal, and then we can find the general linear transformation. So after computing this expression, we are getting a general linear transformation. Once this is done, we can easily compute x, y, z while putting the values. So we got, after simplifying, this is the value of the given transform. So because if you see the basis vector they have given, basis vector map to basis, we will see in the next video later, right? How basis element can be uniquely mapped to the basis element and all those other important properties in further videos. So they have given you the basis element that map to the basis element basically, and then they are trying to, find the general linear transformation using this method. Okay. So now if you see here, uh, the next problem, suppose L is a linear transform from R2 to R to be a linear operator, right? Then L of I plus j equal to this and L of minus I plus 3j equal to this. Then express Li and Lj as a linear combination of I and j. So very simple. Let L of I equal to Ai plus Bj. This is a linear combination. We are representing this L of I. Similarly, L of j can be written as a linear combination of I and j. So A, B, C, D, we have to figure it out, right? Since L is linear, L of I plus j can be written as L of I plus L of j, and which is already L of I is within our hand and L of j is in our hand. We can write them and collect the coefficient of I and collect the coefficient of j, and then this L of I plus j is already given I minus 4j. So we will, compute the coefficient of I left hand side, right hand side, and then equate them. So after computing this, we got a plus c equal to 1, b plus d equal to minus 4. So we have two equations and four unknowns. So we require two more equations and to solve these equations. So second two equations can be obtained using the second component, right? This one with this one I'm going to get. Okay, so now you can just do for this. Similarly, L of minus I plus 3j can be written as L of I plus L of 3j, and since this is linear, so 3 can be out, L of I and L of j. And L of I, L of j we have already been given, so I can write here a plus ib and 3 times of c plus id, and this values is already given. L of minus I plus 3j is equal to minus 6i plus 3j. Again, you do the same stuff as we did before. So to collect all the component, after solving these A, B, C, D, four equations, four unknown, we got C equal to minus 5 by 4 and A equal to 9 by 4. And similarly, we can say D equal to minus 1 by 4 and B equal to minus 15 by 4. So which we can write the linear transformation 9 by 4 I minus 15 by 4j. Whatever the alpha, beta, AB you have taken, A, B, C, D, we are going to just plug in terms of this. So this is all. So thank you very much. Thanks a lot.